Howdy, what's going on? So we're at this 6th of 7 videos in this lecture on potentials and fields. We're out of the fields, actually. We're not doing fields anymore. What we're looking at are sort of energy considerations using the potential. They do similar things to what we were doing with the fields, only now we care about the energy, kinetic energy, the work, conservation of energy, all that fun stuff. We just worked with stability. We were working with stability with a map of the potential. So we had a funny-looking squiggly map of little equipotential lines, and then we decided, okay, now that we've got this nice squiggly map, what are we going to do? We're going to figure out where if I put a negatively charged particle, is that negatively charged particle going to sit and rest and be stable if it has no kinetic energy, right? If I just put the ball there, it's not going to move in that field. Along the way, we figured out where the positively charged ball would be stable as well, so that way we've got the comparison and we understand things all the better. More comparisons, the better we understand things. Got to figure out things to compare if we don't understand things. So next we want to go through and talk a little bit about a more problem-y sort of problem. So I'm going to do an example here. I don't usually like to do examples in slides, but you got to work with what you've got, and today all I have are slides. So we're going to look at this problem. So what I'm going to do is I'm going to shoot a charged particle through here. It's got a charge of small q. This big old guy over here, I'm shooting directly at that big old sphere with a radius r and a charge of big Q. On top of that, I'm shooting it through this plate, and this plate has an electric field coming from it of E. So it's a charged plate, and it's got an electric field of E, which is going to retard the motion. So what I want to do is I want to shoot this thing through there, and I want to not hit that big blue ball. All right, that's what I want to do, is I want to shoot a particle through and not hit the big blue ball. All right, so if I don't hit the big blue ball, what does that mean? Well, I want to figure out that condition. What does that condition mean? And once I have that condition, how do I figure out whether or not I meet that condition, right? What is the critical point for that condition? So those are the two things I want to do. And it's a pretty good idea. It is a pretty good idea, I'm going to say, if you are going to take a look at those things down there. What is the condition? How can I find it? Think about what it is, pause this, write down what you think the condition is, write down how you think that applies mathematically, and then, unpause this. So first, think about this a little bit, write these down, and then pause. And when you're done pausing, come on back and we'll talk about what I think these are. Okay? All right, so what is the condition? What is the condition? Well, what I want to do is I want this thing to stop right at that point, right at the edge of the ball. So if I stop it right at the edge of that ball, then the velocity is 0 there. If the velocity is 0 somewhere beforehand, it's going to keep on going away from that ball. And that means that I could have shot it a little bit faster and still not hit the ball. So I need that as the critical velocity. The critical initial velocity has to end up with the final velocity being 0 right at the edge of this sphere, right at this point right here. So that's where we're going to have to do this. That's what we're going to have to look for, and I hope that you're looking for it. Okay, so how do I find that? Well, basically we're going to do the same thing we did in the last lecture, and that's we're going to use conservation of energy, work, whatever you want to call it. So we're going to use conservation of energy. The energy at this point and the energy at this point have to be the same. Because of that, we're going to be able to use the potential, because the potential is related to the energy. See, the potential energy is just the charge of this little particle that I'm shooting times the electric potential at that point. So I've got all the stuff I need for that. I know what the initial speed is. When it's going through here, it has an initial speed v0. I know the speed over here, that's 0. So I know everything I need to know about the kinetic energy. I know everything I need to know. But as far as the charged sphere is concerned, I also can calculate the potential from this charged sphere here and here, and I can figure out this potentials from this charged plate here, and here as well. So I will do that, and that's how I'm going to figure everything out. All right. Now, this conservation of energy looks like this. It's, this constant energy, this energy constant, because it's conserved, it's constant. We have the sum of the initial kinetic energy and the initial potential energy, and the initial potential energy being the sum of all of the potential energies in the world. All right. Every potential energy that could possibly affect the motion of your object. And that's going to be equal to that final kinetic energy and plus the final potential energy, the sum of those two contributions. So how do we do this? How do we get this done? We do it the same way we did earlier. We make a table, right? I know I've got a kinetic energy. I know I've got two different potential energies. I know I've got an initial and a final. I can just start filling these in. I fill these in, and then I start putting numbers in, or symbols, because I don't have any numbers, but you understand the difference, right? So how does this work? Well, initial and final, well, standard definition of kinetic energy is 1/2 mv squared. That's what it means, unless you're going really, really fast, all right? We're not going to go that fast. We're going to go nice and slow. Take it slow, 1/2 mv squared. And the final kinetic energy has the same form, but the final kinetic energy is going to be 0 because the speed is 0. If the speed is 0, then we don't have any issues. So we've got those two things figured out, lickety-split. Now we need to figure out what the potential energy from the plate is and the potential energy from the sphere, right? So the plate is sort of fairly easy. We're going to use this same idea that we used earlier for that special case of the relationship between the electric field and the electric potential, the potential difference that we used earlier, which is the change in the potential from one point to the other is equal to the minus the electric field, whatever that is, times the separation, the distance from wherever it is to wherever it is. So we're going to look at the difference between here and over here. One thing to note is that the electric field from the plate points into the plate, which in this case would make E negative. All right, so if E is negative, then that's going to make its contribution positive. The difference between the potential at this point and at itself is going to be delta x equals 0, which is 0, right? So the initial distance from the plate is 0. We can use this as a reference point for that field, right? For that contribution to the electric potential. All right. For this other one, we have to figure out what this distance is. Well, this point is not D, because D goes to the center of the sphere, right? And the sphere has a radius r. So we go over D and then we come back r. That's D minus r. So now we have E times the quantity D minus r as the potential. And to turn that into a potential energy, I have to come over here and multiply by the charge of the object that's moving, right? We've got this object that's in the beam. That object has a charge q, so that's where this little q comes from. That's the charge of the object that's moving. The big Q is the charge of this thing up here, and we'll see that in just a second. All right. So now we've got those two contributions. We're ready for our next issue. The next issue is trying to figure out what the potential is here and here, coming from here, just the contribution from this large sphere. Fortunately, outside of the sphere, this sphere acts like a point charge. Okay, so outside of the sphere, it acts like a point charge. Inside, it does not. Inside, it acts according to its charge distribution. We don't know its charge distribution. We're not given that, and we're not going to play with it. We're not going to try to figure it out. All right, but inside this nice uniformly charged sphere, or outside of this nice uniformly charged sphere, everything's going to be a nice simple expression, which is this 1 over r expression for the potential, what we've used over and over and over again. Now we're old hats with it. So I've got the 2 points. One is right outside of the sphere. It's a distance r from its center, so that is what the r variable, the distance, is here. It's the distance from the center to the field point. The field point is right outside of the sphere, which is a distance r, the radius of the sphere from there. And then all the way out here is this D. And so the initial potential from this thing is, well, the initial potential energy is KQ Q'd over D. So little q, of course, again, being the charge of the moving particle, big Q being the charge of this guy. So we're doing okay. We've got everything we need. Now we just have to do all of the math. We got to do all the math. Do you want to do the math? Of course you want to do the math. You love the math. That's awesome. Okay, so here's the math. So the first thing we do is we just substitute all of these 6 numbers in to these quantities. K plus 2 contributions of the potential in each one. So 1/2 mv squared, there we go, plus a 0, that's my 0, plus kqqq over d, there we go, kqqq over d. And then we have 0 for the for the final kinetic energy. We have something from the field here, which is this QE d minus r, and then we have this contribution, which is the kqqq over r, right here at this point, right there. Okay, so after we've substituted, now we can do a math. We can do all the math we want. If you want to think about the math a little bit, why don't you do this? Why don't you pause? Then I'll show you what I got, and if they disagree, you can figure out how to get what I got. All right, that's the deal. So let's do it that way. I'm going to solve for v naught squared. All right, and when I solve for v naught squared, I get all this wonderful stuff. I've got 2 over m because I have m over 2 over here, and then I've got the QED minus R there. I've got this contribution, the KQQ over R here, and then I have to subtract this contribution, the KQQ over D, from both sides, and that gets the minus KQQ over D over here. So that's just a little bit of algebra. That's nothing that you should be scared of. You should never be scared of algebra. Algebra is your friend. Algebra likes you just as much as you like it. And so if you don't like it, it's not going to like you. But if you like it, everything's going to be awesome. All right, so just like what's good for you. All right, that's a bad habit. Okay, and then you just solve for v naught, and you get this equation. You get an equation all the time. It's fun to get equations, but this is the solution. This is where you end if you're just given symbols. Is basically the simplest thing that you can figure out. So how come this is the simplest? Well, I've pulled out a bunch of stuff. Like I've got this common factor of q in all 3 of these terms, so I pulled it out. I figured out that I could combine these terms because they have like 2 or 3 terms in common. They have 2 or 3 symbols in common. So combining them is not a bad idea. So I have 1 over r minus 1 over d, which is d minus r over r times d. So that means I end up with the common term of d minus r in this and the difference of these 2 terms. So I bring out the d minus r. That sounds like it's a pretty good idea because that's a physically meaningful thing. That's the distance between the plate and the ball. That's the closest that they get. And then we have this sum of the field from the plate and this fairly strange looking thing that's field valued, which is sort of the geometric mean of the fields here and here. Why that? Well, I know why because I did it, but I don't know if that means anything. I think it means absolutely nothing. Because I haven't seen that over and over and over again. If something has some sort of physical meaning, you probably see it. You probably see it over and over and over again. That's how these things work. So that is an example about how to work one of these problems. Fun, easy, just move things around. Be systematic. If you're systematic, it's easy to get things right. If you're not systematic, if you're just trying to understand everything at once, then you have a problem. Remember the chess master story, right? The chess master can do everything at once because the chess master's done everything so many times, right? The chess master can memorize that board just like that. The novice can't. So if you're not the chess master, don't try to do everything at once, right? Don't try to memorize the board. Just try to look at each piece and don't make any mistakes, right? Just look at each piece one at a time and figure out what it can do and so forth and so on. After you played 100,000 games, then you'll be really, really good at everything. But don't pretend like you've played 100,000 games when this is the 5th time you've played chess, all right? So we'll talk about things a little bit later when I've decided I'm ready to talk about that last ranking problem. It'll be a fun little ranking problem. I know you'll love the ranking problem because I love the ranking problem. And it's a very, very common sort of problem that you'll see over and over and over again, the kind of thing that loves to show up on quizzes and tests. Okay, so I'll talk to you later. Bye now.